So here's a quick question. Right now, as you're watching this video, do you know how many programs are actually running on your device? Probably way more than you think. Your browser, background updates, Bluetooth, your antivirus, and maybe Spotify too. And somehow, none of them are fighting with each other for your CPU. That's not magic. That's one single piece of software doing insane amounts of invisible workload behind the scenes. That is none but operating system. Today we are going deep into it, what it actually is, how it manages your entire machine in the DSA style concepts. Every CS student needs to know about it, and yeah, we'll use diagrams because trust me, this stuff clicks so much better visually than theoretically. Let's get into it. What is operating system? What it actually does? So here's the simplest way I can put it. Imagine your computer's hardware is really talented but very literal employee. It can do exactly what it's told, nothing more, nothing less, and it definitely doesn't know how to be a polite about it. The operating system is the manager. It's the middleman between you and the user and the raw hardware, the CPU, the RAM, and the storage, all of it. An OS is a system software that manages hardware resources and provides services for application programs. Formally, we can tell you about it this way. But honestly, forget the formal definition for a second and just think of it as that thing that makes clicking an icon turns into a program actually running. So why do we need an operating system? Why do we need one? Could you run a computer without an OS? Technically, yes. That's what early computers did. You had write raw machine code, feed it in, and pray, just pray. No multitasking, no file system, no user friendliness, and whatsoever. The OS exists to solve real problems such as resource management, abstraction, security and isolation, and convenience. So, in the resource management, sharing CPU, memory, devices among multiple programs fairly is the task or the job done by resource management. And in the abstraction, you don't need to know how hard a disk physically store bits, and the OS gives you a nice folder structure instead. Security and isolation. Stopping one shady program from reading another program's memory, it also provides security, privacy. Convenience. A clean interface instead of raw hardware commands is what everybody needs. So basically, hardware is dumb but fast. The OS makes it smart and usable. So the next part is the core five functions. Those are the five functions in OS which every OS performs. So every OS, whether it's Windows, Linux, Mac OS, Android, they all do these five core jobs. The first one is process management, memory management, file system management, device management, and security access management. So while coming to the process management, it decides which program gets the CPU first, how it gets, when it gets, why it gets, if it is based on priority. So in the memory management, allocating and freeing RAM for programs is done. Most of it is done by memory management. File system management, organize your data into files and folders and directories. Everything is managed by this file system management. So while coming to the device management, talking to a keyboard, all of your devices, talking to your keyboard, mouse, printer, GPU, and everything is maintained and done by this device management. So it uses the device driver, it's a small software. While coming to the security and access control, permissions, users, accounts, protection, privacy, all of it is provided by this security and access control. Who to give access, how to give access, why to give it the access for this particular person or user. It's done by this. So we are going to each of this, right? We are going through each of this, but let's zoom out first and see how they all sit together architecturally. So this is how it works. First part is application, and then system interface, kernel, and then hardware. So OS is basically it's an interface between hardware and application, which is nothing but user. So here it maintains the user mode, and at the kernel it maintains the kernel mode. There are multiple layers involved in it. See how clean this is, right? Your apps never touch hardware directly. That would be chaos and a massive security risk. Everything goes through the system call interface, gets handled by the kernel, and only then touches actual hardware. So the kernel is the real boss here. It's the core of OS running with highest privilege level on your machine. It manages most of the tasks. So as we have discussed what is OS, why it is necessary, and the layers of OS, basically architecture of OS. Now let's talk about different types of OS. So not all OSs are built in the same way. Let's go to the main types quickly once. So here are the different types: batch OS, multi-programming OS, time-sharing OS, distributed OS, real-time OS, and mobile OS are the different types here being discussed currently. So in the batch OS, it is really old school. Jobs are grouped and processed with zero user interaction. Think punch cards, 1960 vibes, right? So these old school batch OS batches most of the jobs and performs it at once. So because of these, that won't be an optimal solution for an OS. And coming to the multi-programming OS, this is currently used in most scenarios. Multiple programs sit in memory at once. The CPU is never idle. So it just continuously works and implements number of programs. And while coming to the time sharing OS, the CPU rapidly switches between users' tasks, giving the illusion everyone is running simultaneously. So in the current period, we are using this multi-programming OS and time sharing OS as multiple programs, and the switching of CPU between number of tasks and programs which are currently implementing is done simultaneously. Both of this work together. While coming to the distributed OS, it manages a group of separate computers. In a sense, it makes them feel like one system. Even though they are distributed, it makes them feel like one system. So the real-time OS, I'll come to the next type of real-time OS, used to where timing is everything. Like a pacemaker or industrial machine. If we miss a deadline, it isn't just annoying, it's dangerous. You know what I'm telling you? Hopefully you're understanding what I'm telling you. So welcome to the mobile OS, Android iOS, Mac iOS. So all of it are being part of this mobile OS. So it helps with optimized battery control, touch, constrained resources too. So the next concept is kernel types. Let me tell you one more thing. Most modern desktop OS are technically multi-programming and time sharing at the same time. So as we have already discussed, I am just highlighting this sentence because if it is a part, you should understand. And I'll come into the next concept, kernel types. So it is important but distinction. There are multiple types as you can see: monolithic, microkernel, hybrid. So what is monolithic kernel? It almost runs everything. Device drivers, file systems, memory management in one privilege block. You're understanding, right? In one privilege block, it runs most of the tasks being assigned to it. Linux is classic example. So fast, but a bug in the driver can crash the whole system. So we must be really careful while performing these tasks. So an example as we have given is Linux, must have been used. So if you want tutorial on Linux, comment down below. Next one is microkernel. Keep the kernel minimal, just the bare essential like communication, basic scheduling, and push everything else like drivers into a user space. More stable, but there's more overhead from all that communication. While coming to the hybrid kernels, it's more like Windows. So it's blend of modern commercial OSs and it can be used in most scenarios in the current period. Well, coming to the next concept, it's process management, which is nothing but the heart of OS. What is a process? Process is nothing but program under execution is process. So alright, there is, this is what it gets genuinely fun. a process is just a program in execution, right? Your program on disk is passive, but when the moment it hits, when it starts running, it becomes an active process with its own memory, state, and resources. The passive part, it becomes active soon after it starts running. So every process goes through a life cycle. It gets created, waits its turns, runs, sometimes has to pause for different, something like disk input, eventually it finishes. This is one of most tested concepts in OS interviews. So let's actually visualize it. So here's a diagram, the process state diagram. So in this we have new, ready, running, and between ready and running it also checks for waiting state, and after which again it checks for running, and then it gets terminated only after it has executed. And if after it has ran the program, then it gets terminated, the process gets terminated. So to follow this, a process is born as new, then sits in ready, basically, raising its hand saying pick me. Once the scheduler picks it, it goes running. Now, there's the interesting part. If it needs something like reading a file from this, it can't just sit there wasting CPU time doing nothing, right? So it goes to wasting. Like it goes to first after running, after ready running, and then it goes to waiting, not wasting time. Once that IO finishes, it doesn't come straight into the back to running, right? So it goes back to ready first, and then it waits. It turns again fairly, eventually it finishes, and then it's terminated. So this exact program shows up constant OS exams. So if you remember one thing from this video, remember this. Basically, new, ready, running, terminated. Between ready and running, waiting state is mandatory. It checks whether IO is complete or needs IO. So the next concept is CPU scheduling algorithms. In CPU scheduling algorithms, now when there are multiple processes in ready, who decides who goes next? Why it goes next? So that's the scheduler's job, right? And it uses algorithms like these, like FCFS, SJF, round robin, and priority. FCFS is nothing but first come first serve. It is simplest way possible. Whichever comes first, those influenced and get implemented first. So it causes a convoy effect. Even the first come, the process is much larger compared to the next come. It has to be implemented no matter what, because the first come and first serve, it follows the ideology of first come and first serve. And the next part is SJF, shortest job first. So as we have discussed, a longer job and a shortest job, even the longer process has come first, we'll be avoiding it, and first we'll be implementing the shortest job first. Only after that, we'll be implementing the longer job first. Longer job next. Picks the most task next. Like minimizes the average waiting time, but you need to know execution time in advance, which is basically unrealistic, right? So I'll come into the next thing, round robin. Every process gets a fixed time slice. Then it's cut off, moved to back of the queue basically. So this is what most time sharing OSs actually see and use. So priority scheduling. In the priority scheduling, which process has higher priority will get implemented first, irrespective of about starvation or anything. So higher priority process goes first, but you have to watch out for the starvation. Where low priority process never get their turn. So if they ask which is best, the honest answer is it depends on system's goals. Throughput, fairness, response time, there's no single winner for it. Hope you're understanding. As I've said, there's no single best algorithm. It depends on most of the factors and your requirement. I'll come into the next concept, memory management. In the memory management, it's a big topic. You have to understand it, so listen carefully. Memory. Your RAM is limited, but you are running dozens of programs. How does that even make it? No explanation. What is the explanation for it? How does it even work? So it works based on paging, segmentation, and virtual memory. Paging. memory is split into fixed size blocks called pages. Let me show you. So look at this. The operating system have number of frames and pages. These pages are nothing but fixed size blocks. The memory splits it on its own. We don't have to do much of it. A physical memory into frames is the physical memory, and the memory is split into fixed size blocks called pages, and the physical memory into frames. The OS keeps its pages mapping table. In the mapping table, it maintains all of it in the mapping table and it maps continuously. So process doesn't need to sit on one continuous memory block, It doesn't get lost. It continuously gets mapped and it implements on its own. While coming to segmentation. Segmentation divides memory based on logical units like code, stack, data. More aligned with how programmers actually think about memory. Let me tell you, virtual memory. In this virtual memory, generally one of the coolest OS concepts, it lets your system run programs larger than your actual physical memory RAM. You're understanding, right? Rather than your actual physical RAM, it helps you to run the programs that are larger than this physical RAM by using disk space as an extension of memory. So this is why you have 8 GB RAM but still technically use way more than it. So as we have discussed paging, segmentation, virtual memory, we have furthermore topics on this paging, which is nothing but page replacement and thrashing. These pages must be maintained in a good and continuous way. So this page replacement, if physical memory fills up the OS, it has to decide which page to kick out to make room, right? So all of the pages can't stay at the same time. One has to move out for the other person, for the other, to make space for other page to get in and do its job, right? So which page to kick out or which page to remove, to eradicate, will be decided by this page replacement algorithms. So algorithms here include FIFO, LRU, which is nothing but least recently used, and optimal replacement. If your system is spending more time swapping pages in and out than actually running programs, that's called thrashing. So it's basically, it's wasting its time on its swapping its pages rather than doing its actual job. That is thrash. And it's one of the classic causes of computers that suddenly feels painfully slow even though nothing's crashed. So our next concept is deadlocks. It is when a process gets stuck together, number of processes get stuck together. I mean, like they get connected to each other and they are stuck forever. This one it trips up a lot of students. It's a bit of confusing concept, but let's slow down. A deadlock happens when two or more processes are stuck waiting on each other forever. I mean, like nobody can move. There are the four conditions must all be true for a deadlock to happen. So these are the conditions: mutual exclusion, hold and wait, no preemption, and circular wait. In the mutual exclusion, a resource can only be held by one process at a time. I mean, like when process is being executed, it can hold only one resource at a time. So while coming to hold and wait, a process holds one resource while waiting for another. So while it is waiting, it just works on one resource which is available for it. No preemption. Resource can't be forcefully taken away. It can't be, just given away or taken away. Circular wait. Process A waits for something process B has, and B waits for something A has. Classic. It's a classic real world analogy I'll give you. Two people at a narrow doorway, each insisting to go further. They are waiting for other to go ahead, both refusing to move. That's a deadlock. So how do we deal with it? Prevention, avoidance. We can also use Banker's algorithm. So we'll discuss it further. Detection with resources allocation, graphs, or just recovery. I mean, like killing a process to break the cycle would work fine. Let me show you how it actually is being implemented here. So this is a deadlock over here. Resource 1 is being assigned to process 1 while the process 1 is waiting for resource 2, and here the resource 2 is assigned to process 2, and the process 2 is waiting for resource 1. So process 1 and process 2 are assigned to resource 1 and resource 2 respectively, but these process 1 and process 2 are waiting for resource 2 and resource 1 respectively. What they have is not necessary for them, I mean, like, it's not sufficient for them. They have been already used with those resources. They want something else with some, that some other resource have. So what they are doing is they are waiting. While waiting, they are forming a deadlock over here. So our next concept is file system. Over here, the file system, this file system is how your OS organizes data on disk. It's not just folders or files visually. Under the hood, it's managing directory structure, file allocation, metadata, and number of common file systems here. So in the directory structure, it's a hierarchy of folder file system. And while coming to the file allocation, how file data blocks are physically placed on disk. I mean, it can be contiguous, linked, or indexed allocation. Metadata, data about itself is nothing but metadata. So here the data is file, right? So metadata is nothing but about file, whatever the information is available, like file size, permissions, timestamps, all of that is maintained by this metadata. Common file systems. So Windows, Linux, APFs, on macOS, everything is maintained by this common file systems. The next concept is I/O management and device drivers. While coming to this I/O management, your OS also has to talk to wildly different hardware, right? So it can be a mouse, a printer, a GPU, a webcam with all different speeds and protocols. It does this through, device drivers. Not only just device drivers. Basically, it's based on device drivers, but it also uses a number of other things too. So here device drivers are nothing but a small piece of software that translates generic OS commands into a hardware. So it's nothing but specific instructions it has to follow. There's also interrupts. So in this interrupts, it defines as, instead of CPU constantly checking, is the printer ready yet? Is it done yet? Or questioning continuously, which is waste cycles. Like, hardware sends an interrupt signal that moment it's ready. Rather than questioning continuously or wasting cycles, the CPU jumps to handle it immediately. Much more efficient, right? That is how this polling and interrupt. What is polling? So polling is nothing but, it just questions, is the CPU printer ready? Is the printer done yet? Is it ready yet? Is it, we can use it? It questions continuously. That is polling, which is waste cycles. So these interrupts and pollings are also present in this I/O management. The next concept is kernel mode and user mode. So one more critical distinction is your CPU actually has privilege level. It is kernel mode and user mode. Kernel mode has full access to hardware and can execute any instruction, but the user mode is restricted. Your application run here and can't directly touch the hardware or other process memory. So that is how it has been implemented since long. This is security feature, not a limitation, right? So if a random app could directly write any memory address it wanted, malware would have a field day, right? So every time your app needs something privileged, reading a file, like reading a file, allocating memory, it makes a system call which briefly switches the CPU into kernel mode to safely handle all the requests being made by the CPU, then switches back to whatever mode it has been assigned to. So our next concept is popular operating systems compared. So currently we are using, on our systems we use Windows, we use macOS, we use Linux, we use Android. In a quick real world tool, Windows dominate desktop with a hybrid kernel and huge software compatibility. And macOS runs on a Unix based hybrid kernel, XNU, which is nothing but Unix based hybrid kernel. So in this, with tight hardware software integration, since Apple controls both, so with the help of this Linux, monolithic but modular, popular most of the world's servers, and is fully open source. Android built on Linux kernel but optimized for mobile and battery life. So different priorities, same underlying OS principles, and it can work more efficiently too. So Android currently, which is being implemented on our phones, and I mean like OS, it's a good concept. If you understand it and if you work on it, it helps you to understand how the internal system, internal software is being implemented. And it's major concept, major topic too. So I mean like if you're preparing for your tech interviews, OS concepts show up constantly, especially process scheduling, deadlocks, memory management. Even outside interviews, understanding this stuff makes you genuinely better engineer, because I mean like you finally understand what's happening with your code when it runs slowly, your apps hangs, and your system starts thrashing. So let me give you a recap. So we have discussed how what OS manages, how it helps with the process management, memory management, all of it, how process moves, what are the states of it. There are different states here: new, ready, running, waiting, terminator, all are the different states. So how it goes with the process and program scheduling, why do we need to schedule, memory management, how the deadlocks happen, and the kernel mode and user mode, different modes, how it switches between these two.